Okay, good morning. We are going to do first time at NANOG Optical Networks 201, building optical networks. I'm Sergio Rothenstein. I'm Director of Product Line Management with MRV. You can see us at Beer and Gear. And what we are going to talk today, it's about simple optical networks, about do-it-yourself versus lead services, your choice, about the optical network solutions, basically talking about basics, about design rules. We'll have some examples, simple examples, and show how to do it. We'll talk about the networking elements, the optics, the transponders, muxponders. We'll touch just one slide about dynamic optical transport, just to show that there is more beyond the simple optical transport. And we'll talk about our view of 100 gig evolution into 2014. And we'll close with some operational expenses, OpEx choices. Just when you do it yourself, what should you look for? So when you want to do optical transport between two data centers or two locations, you have basically two implementation options. One of them, just get lead services. You get all the services, all the elements, fiber, and the full connectivity, the equipment, everything is provided by a service provider. From your point of view, it's the simplest solution. Simple to manage. You do nothing. The service provider chooses the equipment, installs, configures, provisions, and provides all the services. You need no knowledge, no skills, no knowledge about optical transport. But you have the monthly payments for renting the equipment and for renting the services. The other option is to do it yourself. You somehow get hold of a pair of fibers, you own it, or you buy it, or you lease it. You then select some optical transport equipment, and then you have to operate, to manage, and to install, to provision, and you need some level of knowledge and skills in order to do this. At the same time, the benefit is that you're not going to pay to rent the equipment. It's yours. And if you buy a piece of equipment that allows you to grow, you can just grow as you need more bandwidth. You expand your network. So is this do-it-yourself optical transport scary? It's complicated. No. Basically today, optical transport at this level, it's a simple application. The optical elements that go into an optical transport, most of them are standard, covered by multi-service, multi-source agreement, and they will interoperate. You get an SAP, an SAP Plus, a DWDM SAP Plus, or an SAP, and you have a very good chance that it's going to work in other type of equipment. You just must pay attention to some details. This type of optical transport is mostly plug and play, and you have such a choice of suppliers that drives the cost down, so it's beneficial for you to do it yourself, and of course for us. Looking a little bit at diving into the elements of the solutions, let's look at protocols. 10 gig. In principle, Ethernet and 10 gig Ethernet is the king. It's the protocol of choice. Then in the data center, mainly between routers, you're going to have 40 gig, pretty expanding. And you'll have very infrequent presence, very unusual to have 8 and 10 gig fiber channels, and more than that, InfiniBand. Now, regarding the 100 gig, that's the main question. It's an emerging, and it was emerging for quite some years, but it's today a reality. And what we foresee is that 2014 is the year, and we'll show you why. It's the year when 100 gig is going to become a common choice in optical networks, in metro and data center interconnect. It's going to become a common technology and not something that is fancy and unusual. The optical elements for this simple transport are, first of all, pluggable DWDM transceivers. XAPs, SAP Plus, and now CFPs. Then you have the layer of multiplexing, the MUX and DMUX, that merge all the wavelengths together. And if you have longer links longer than the native capacity of the optics, then you can employ amplifiers and dispersion compensation. So a couple of transport services, and by chance I had the figures for 100 gig, but can be any rate, can be a 10 gig. Starting with simple media conversion, because that can be very common in your applications. You have two sides. You have multimode on one side and single mode on the other side. You must convert from one to another. So you basically must put a multimode to single mode conversion on the multimode side and go all the way to the other side. Same for distance extension. You have two interfaces of multimode. You have a long link that goes beyond the reach of the multimode. You must have a media conversion from multimode to single mode and then do distance extension. Going to DWDM, same two locations. Take a few wavelengths, 1, 2, or 80, and just multiplex them together on the same point-to-point link, and you have a DWDM link. And we can migrate to 100 gig today and get to an incredible capacity of 8 terabit or even 9.6 terabit using 80, 100 gig wavelengths. So all these real services that are deployed and will be deployed in 2014. So let's look at the options of implementing this optical transport. Simplest one, put your DWDM transceivers in the switches. Nothing wrong with that. It's the simplest optical transport. Add a layer of multiplexers, and if you have longer links, of course you'll have to add amplifiers and dispersion compensation. The other side, it's add an independent optical transport layer. So you have the DWDM transceivers in transponders, in modules that do the conversion to DWDM, and then the same elements, the MUX, DMUX, longer links, amplifiers, and DCM. They look quite the same, just you have an intermediate layer of transport in the middle. And now comes the main question, how do you choose? How you as users of this optical transport are choosing between the two options? Why to do A or why to do B? Would be interesting to hear you guys, if anybody has any answers to these questions. Sure.
Your hardware may not support the different transceivers in it, so you may have to use the optical transport system.
Thank you. Anybody else? Manix.
Well, rather than have all the added electronics in between point A and point B, if you're going on like a campus model between one building across town and another, it may be cheaper, easier to maintain, and more effective to just use the DWDM optics within your router or switch. And I mean, there all you need is a passive MUX, and you're done.
So you're basically voting for the left side.
It's application dependent which one you're going to
Right.
use. But you know, as far as you're saying, what reason would you have to choose one or the other? If you're in a short span, doing that very simply.
Absolutely.
Yeah. If you're going long haul, if you have a need to drop a wave out in the middle, then you may not want to. You're going to be forced to have some electronics in there. If you're going, if all your channels are going from one spot to the next, if you're designing like a hub and spoke, something, then the DWDM optics will still work. If you don't want to have the DWDM optics in your gear because that does present a certain problem with sparing, then obviously you're going to want to have electronics. But there's a significant capital expenditure in having a whole bunch of transponders.
Absolutely. Appreciate it. Okay, thank you. So just going over the basics of optical transport, defining wave division multiplexing. That's basically a method of carrying more capacity over a pair of fibers by assigning the incoming optical signals to specific frequency of lights. Those are the wavelengths or lambdas. And combining those streams together generates more bandwidth. And every data stream has its own virtual fiber, its own virtual lambda. You have in the industry two types of WDM, coarse division multiplexing using 20 nanometers spacing. And that defines per ITU standards 80 wavelengths in the range of 1270 to 1610. DWDM on the other side spaces more closely. I think the limit is 1.6 nanometer, covering typically the C-band and possibly in the L-band. And you can get, depending on the spacing of 150 gigahertz, 40 to 48 wavelengths, channel 17 to 61, or 80 to 96 wavelengths, same 17 to 61, but now centered and half frequencies in the middle. And good for us, DWDM optical signals may reach extended distances through amplification and through impairment management, amplification and dispersion management. So let's look at the basic parameters of an optical transport. First of all, optical power is measured in decibels. Signal optical power is measured in decibel dBm, decibel microwave, microwatt. And the fiber link or loss from A to B, it's in dB. You have a power loss, you incur an attenuation, it's negative dB. You have a power gain, let's say an amplifier or transceiver, it's a positive dB. Typical in C-band, you consume about 1/4 of dB per kilometer. Those are the basics. And in general, when you do an optical design, leave a little bit of margin beyond what your calculations are. So let's look at the basic optical budget. It's based on minimum transmit power and minimum receive sensitivity. So looking at the example, we have a transmitter of 0 dBm, a receiver of minus 23 dBm. We have an optical budget of 23 dB. If your link basically generates attenuation beyond this optical budget, you are prone to have errors. And in general, network design, it's not based on distance. It's based on measuring your optical budget and requirements of your fiber. Now, who are the consumers of this optical budget? Anything that generates attenuation. The main culprit, the fiber loss. You have 10 kilometers of fiber, it's going to generate fiber attenuation. Then you have all the other elements that can be simple attenuators or max-demaxes or dispersion compensation modules, connectors, splices. Everything that is on the way is going to generate attenuation, is going to consume your optical budget. Optical impairments like dispersion are translated, not sometimes, are translated into an optical attenuation or into a penalty. Luckily enough, the attenuation can be compensated by amplifiers. So let's look a little bit talk about dispersion caused by two phenomena in fiber. One is polarization mode dispersion, and that's caused by the two polarization states of the fiber that have different speeds, different velocities. Then you have the chromatic dispersion when the different wavelengths travel through the fiber at different speeds. Both phenomena of variance in speeds cause basically spreading of the light pulse. And you see the picture basically, this spread of the light pulse. This is basically affecting not just DWDM, it's not about DWDM, it's about light traveling through the fiber, so affects also a single channel. Don't think it's only DWDM. As the pulse spreads into the fiber, it's basically difficult to be recovered. The symbols are difficult to be recovered by the transceiver, receiver, and they basically cause inter-symbol interference. Now, the level of degradation depends, first of all, on the quality of the laser that it's used, on the spectral width of the laser or chip. Of course, bit rate. If you have a 1 gigabit per second data transfer or 100 gigabit per second data transfer, the bits are going to be much narrower and closer together on the 100 gigabit, so the phenomena of dispersion is going to be much higher. And of course, on fiber type, you have various types of fiber. Some of them have cause more dispersion, some of them cause zero dispersion or low dispersion. How do you compensate for? Mainly for the chromatic dispersion. As I mentioned, special fiber, you have those two types of fiber. One is zero dispersion, the other one is low dispersion. That can help manage this dispersion. And then you can have dispersion compensating fiber. You basically put a small spool of fiber that causes the signal to go back to the nice shape. And the same phenomena, compensation is done by a dispersion compensating module that has fiber grating inside. Let's look at the transceiver parameters that are basically the basis for our optical budget. Transmit and receive power. Here in blue, I show the 40 kilometer and an 80 kilometer, both 50 and 100 gigahertz. Look at the transmit and receive power, the one in blue. You see that the starting point, the transmit power, is very similar for both of them, for the 40 and 80 kilometer. The main difference is in the minimum receive power. One is minus 16, the other one is minus 23. So that's the difference in reach, or capacity to reach. The minimum transmit power and the minimum receive power, as you remember, defines the optical budget. The maximum receive power states that above this value, the receiver saturates and does no longer recover properly the signal. So it's not good to pass this threshold because then you're not going to recover the signal. Now having in the red circle the dispersion tolerance. Dispersion tolerance, it basically defines the dispersion limited transceiver reach. It's measured in PS per nanometer per kilometer. And every piece of fiber, every type of fiber has a fiber dispersion coefficient. The standard SMF28 fiber generally has a coefficient of 17 or 18 to 20 PS per nanometer. And having a dispersion tolerance of 800 divided by 20 leads us to the 40 kilometer theoretical reach. And this varies with rate. This is typical for 10 gig Ethernet. If you increase it to use FEC rates like 11.3, the dispersion tolerance is going to be lower. Now the dispersion causes, using this dispersion tolerance of a native dispersion tolerance of a fiber, causes basically indirectly to lower your optical budget. You have a dispersion penalty, in a sense, lowers the level of sensitivity of the receiver. Because the minus 16 and minus 23 is basically measured when you have no fiber in the middle. It's what it's called back-to-back. So now your optical budget is minus minimum transmit, minus the minimum receive, and minus the dispersion penalty. Now the main question. We can have fixed wavelengths, 40 or 80 channels, or tunables. What do you guys prefer? How do you choose between them? Do you prefer to pay more for a tunable and have a great inventory management, or you prefer to reduce your capex but deal with the availability and inventory management of fixed wavelengths? Anybody?
I think you would go with the tunable option because then you can decide upon how far you want the wavelengths to be spaced apart based upon the traffic you expect to push through the fiber.
Okay, thank you. Benix gets some exercise.
We did fixed channels at one point, determined it was finally unworkable when we ended up with a unacceptably high failure rate among the transponders, combined with the fact that for reasons we still have not been able to explain, there were certain paths of fiber where we could not run certain channels because of whatever was going on inside the system. So, tunable is always for us. The other advantage of that is the fact that the tunables usually output slightly higher higher power and help us be able to push the signal a little bit further. And some of the paths that we're on, either we're extending maximum distance or the only path we could get was the only path we could get, and we had to take whatever was there.
Sure. Tunables in general, they can be amplified to about 6-7 dBs more than fixed wavelengths. So reach is an issue, yeah.
And what I think the best reason for tunables is that when I ship something to halfway around the globe, I send one tunable as a spare.
Sure. So basically inventory management and ease of access to any wavelengths trumps the cost. Okay, thank you. Let's look a little bit at the elements of an extended link. We have transponders, and for me transponders means optics inside a switch or optics inside a wavelengths module. We have the muxponders that basically aggregate multiple lower signals to a higher rate. Take a few gigabit Ethernet multiplexed to a 10 gig. And then you have the multiplexing elements, mux, dmux, that aggregate and separate the optical wavelengths. We talked about compensating for dispersions, and that's the DCM. And we have the amplifier that compensate for attenuation and get our optical budget to a higher level. Based on the position, and you see the picture there, you have at the beginning of a link a booster optical amplifier, then in the middle it's called an inline, and then just at the edge of the link you have a preamp, and you have there the DCM before or after the preamp. So let's talk a little bit, just a tad about dispersion compensation. Typical today is fiber grating module. It's a small module that compensates for fiber dispersion. Very low insertion loss, that's the advantage, about 3.5 dB. And interesting, and that's applicable up to 10 and maybe 40 gig, but it's a disadvantage in 100 gig installations. If full dispersion compensation is done, the dispersion penalty is recovered. So I have an example here. You have a link of 90 kilometers with a transceiver of 80 kilometers, and we are going to talk in kilometers, even if we should talk in PS per nanometer. But if you had a DCM of 10 kilometers, you're going to still pay the 3 dB penalty that we mentioned before. If you had a DCM for 90 kilometers, you recover those. Your dispersion penalty is going to be 0. So if you need those, 3 dB, that's a good way to recover. And again, that's good for 10 and up to 10 and 40 kilometer, 100 kilometer, it's a different story. 100 kilometer coherent optics like dispersion. About amplifiers, we put some amplifiers here as examples, and we are going to look at different parameters. The most common in the industry are EDFA, erbium doped fiber amplifiers, and based on the position in the network, in the link, you are going to have boosters, inline preamp. We talked about this. Typically, it's in automatic control gain. The gain is always fixed. The amplifier tries all the time to get you that gain. You can have full C-band, and that means it can handle the full C-band, because the gain of an EDFA is unequal per wavelengths, and then you have to flatten them so you get to the same gain. And if you have just a few wavelengths of a single channel, you don't need this flattening, so that's the differentiation. Now let's look at the parameters. Gain, it's signal amplification, and you can have a fixed signal gain amplifier or variable gain, programmable. Shown there in the red are basically two parameters, the gain and the saturation. Saturation is maximum aggregated power. So regardless of how many wavelengths you have and what's your gain, you are going to saturate, that's the maximum output that you are going to get out of this amplifier. So that may limit the per wavelength gain. And I have an example there. Let's assume we have 40 channels that the transceiver has 0 dBm. The aggregated signal of 40 wavelengths leads to 16 dBm input power. Because your output power is 18 dBm, 80 dBm, you're going to have per wavelength gain of only 2 dB. That's it. So in order to, if you need more than that, you need to go to an amplifier with a higher maximum output. minimum input or the sensitivity, of course, below this value, the amplifier is not going to function properly. And maximum input, again, above this, the amplifier will not function properly. And another important parameter that is less significant for the type of examples that we are going to go over is the noise figure. Noise figure is basically the difference in dB between the signal level and the noise level, and the smallest value, it's better for an amplified network. In general, you must, based on optical design, on fiber measurement. Do not just look at kilometers like we are going to do now, yeah? But measure the fiber, get an OTDR, measure your chromatic dispersion coefficient, measure your PMD. And for multi-chain EDFA, of course, OSNR values, optical signal to noise ratio, must be evaluated and controlled, and we are not going to talk about this because that's a little bit beyond this presentation. So let's look at the simplest optical transport service, the media conversion and distance extension. With today's bandwidth of 10 gig or 40 gig, one line is going to be maybe quite enough. Maybe just a multimode to gray optic, dedicated fiber interconnecting the two sides. And that's about it. Now, think about your future and invest in a multiplexing elements and use one of the wavelengths as media conversion, as your single mode transceiver, because you may want in the future to expand your network. And by doing this, you're not going to disturb the existing infrastructure. Now let's look at a simple example of doing WDM, 25 kilometer point-to-point, using 40 kilometer 10 gig optics. So we are starting with 10 gig optics at 0 dB, at 0 dBm. The 40 channel max Dmax is going to add or reduce your signal by 3.5, adding an attenuation of 3.5 dB. And that's bringing the signal to minus 3.5. Then you have the 25 kilometer of fiber that, let me close this guy, that basically is going to add you an attenuation of 6.25. The margin of -1, we are at minus 10.75 just before the Dmax. Dmax adds another 3.5 dB of attenuation. My signal is at minus 14.25, just in line with my receiver sensitivity of minus 15. So we made it across the fiber line. That's basically how you're doing the basic design. Now let's look now at the capacity to implement a 40 kilometer point-to-point using both 40 kilometer pluggables and 80 kilometer pluggables. And now basically we're going to have the choice of using cheaper optics and adding an amplifier, or using the more expensive optics. Same type of calculation. We start at 0. The max adds an attenuation of 3.5 dB. And then we have the 10 dB attenuation of the fiber. Margin of 1 dB, I'm at minus 14.5, just adding all this. For 40 kilometer optics, I'm just at the edge of my sensitivity of minus 15, including the dispersion penalty. So I need to amplify. So basically, I added an amplifier of 10 dB, and that brings my signal back to life at minus 4.5. A 40 channel Dmax gets my signal back to minus 8 dBm, and that's nicely within the active range of the transceiver. Let's look at using 80 kilometer optics, and it's the same calculation. I don't need the amplifier. I'm getting basically to minus 18.25. Keep in mind, 80 kilometer optics have a sensitivity of, effective sensitivity of minus 20. So I'm within the range of my 80 kilometer optics. So the empirical cost calculation shows that if your number of channels is above 8 channels, you are better, you are economically better to use 40 kilometer pluggables and an EDFA. Let's do a 60 kilometer, and what's the change here? Being 60 kilometer with 40 kilometer optics, I'm going to have not enough dispersion tolerance. So I need to add not just amplification, but also dispersion compensation. So if you go over the chart, it's basically the same. The transmit power is at 0. The 40 channel max adds me minus 3.5. Then 60 kilometer fiber is minus 15. I'm putting a margin of minus 1 dB, and I'm at minus 19.5, well outside the range of the 40 kilometer transceiver. So I'm putting an amplifier of 20 dB of gain that brings the signal back to plus 0.5. My DCM that provides the dispersion compensation contributes an attenuation of minus 3.5, that's minus 3. The Dmax minus 6.5. I'm back within the range of active range of the transceiver. Now, looking at the 80 kilometer optics, it's exactly the same calculation. I can use a lower grade amplifier of just 10 dB because I have more sensitivity. I don't need a DCM because I have enough dispersion tolerance. Again, doing the economical calculation, an empirical number is somewhere around 16 channels and beyond. I'm better off economically using 40 kilometer optics and an EDFA and dispersion compensation. And I dare to do the same exercise for 80 kilometer, an 80 kilometer link, even that I put it in red, the 80 kilometer, I still prefer to use the 80 kilometer optics, but theoretically this is doable. Going over the chart again, starting at 0 dBm with the transceiver, the max adds me minus 3.5, the 80 kilometer fiber minus 20. Then I am adding a little bit more margin because it's a longer link, so I'm at minus 25.5. 20 dB of gain brings my signal to minus 5.5. DCM and the channel max, I'm still at minus 12.5, and that's above the minimum sensitivity of minus 15, so I should be okay. On the 80 kilometer side, I don't need any dispersion compensation. I have exactly the same amplifier, and I'm coming just because I don't have the dispersion compensation at minus 8.5. And that's within the range of active range of the transceiver. So the empirical economical calculation says that if you dare to do it, and I prefer to use the 80 kilometer optics, you can use 40 kilometer pluggables, DCM and EDFA, because it's more economical. Now I wanted to touch about how to implement protection and, again, optical design calculations. The left one is an optical per wavelength, so optical channel protection that's done by doubling your transponder, so doing transponder redundancy within the transponder or full hardware redundancy. The interesting part is and the calculation is exactly the same like for a simple channel. The interesting part is when you do optical line protection for the aggregated signal, basically after the max Dmax. And this is done by adding a protection switch, and you have a primary and a secondary that switches based on fiber loss or link loss. So going over the calculation, and you're already used to this, start at 0, the max minus 3.5. The protection switch by itself induces on the transmit side minus 3.5, we're at minus 7. 60 kilometer of fiber, we're at minus 22, margin of minus 23, and we're adding an amplifier of 20 dB, we are back at minus 3.5. Now the DCM, the minus 3.5 insertion loss of the DCM that you've seen already, and then the protection switch, the receive side, it's about minus 2 dB, we are at minus 9. The 40 channel max Dmax, minus 3.5, we are back at minus 12.5 within the range of the transceiver. So we are good. We can do the same on using the 80 kilometers, and the only difference is that we don't need any dispersion compensation, so that line is blank, and I'm coming at minus 8. So again, within the range of the active range of the receiver, we are good. Again, in these cases, it's possible theoretically to do the 40 kilometer. I personally prefer the 80 kilometer option. Looking at transponder choices, and that's external transponders, not inside the switches. The simple transparent 3R, layer 1, retime, reshape, and retransmit. This is the most cost-effective option. Bit error rate within the standard industry ranges of 10-12, 10-14. Multi-protocol, 10 gig Ethernet is a must, LAN 1, LAN PHY and Wi-Fi, but also fiber channel, all the rates of fiber channel, InfiniBand or SONET or SDH, it's interesting to have. It's low latency. In general, it's in tens of clock rates, meaning 10 or 20 to 30 nanoseconds. Generally, you have no SLA tools. You don't have performance monitoring. It's transparent. You have no counters. But you start to see integrating link testing capabilities. So you can test the link prior to installation and get errors while you're testing. And emerging signal quality monitoring, basically looking at the quality of the signal and doing a grading, giving a grade to what is called the IMASC, the quality of the signal. And we start to see these features appearing in optical transport. Moving to the next one, layer 1.5, it's the OTN framing and with FEC encoding. Of course, there is some premium versus the transparent one in cost. If you consider point-to-point, the same point-to-point application, the bit error rate suddenly jumps to 10-18 and above. So for whoever values this, that's important. Same level of multi-protocol as enabled by the OTN generic framing. You have a lot of SLA tools. In general, you are receiving performance monitoring on access, but you are receiving uniform, and that's important, uniform OTN and FEC performance monitoring. So regardless of what you are transporting, you have the same performance monitoring on the optical link. Same emerging integrating link testing capabilities and IMAS grading for signal quality, optical signal quality. And the last one, carrier Ethernet aware. Basically, you have a transponder that has inside an Ethernet switch, and its carrier Ethernet switch has carrier Ethernet capabilities. Preferable to do a low latency, what is called cut-through. Start transmission before the packet is fully received, and that's going to lead to latencies of hundreds of nanoseconds versus milliseconds or microseconds. So bit error rate is standard in the industry, 10-12 and above. It's Ethernet only. You cannot do anything else unless you do conversion to Internet. And you have an extensive standard carrier Ethernet SLA assurance tools. This is classical in the carrier Ethernet, not just the performance monitoring, but mostly the OEM-based tools for measurement of available bandwidth latency. You'll see full, in most of these type of transponders, you're going to see carrier Ethernet solutions, you're going to see full capability of generating packets and flexible packets at line rate and measuring the latency and the lost packets and so on. So now the question, how do you choose between the options? What do you guys prefer? Any ideas? Okay, we'll jump over. Max bonding. Max bonders, as you guys know, aggregate multiple services into a single better utilized wavelength. And that wavelength then goes over the WDM, through the WDM multiplexing scheme and goes on the fiber. Typical example, take an 8 gigabit Ethernet aggregated to a 10 gig optical line. And if you want to go next in line, you basically can combine the 10 gig Ethernet with some 40 gig, generate a 100 gig line, but that's the idea. You can have basically TDM or OTN based and packet based. And the idea is pretty similar. OTN, has defined an elegant way to do multiplexing. You employ FEC, you're getting an excellent bit error rate. It's multi-protocol, supporting all the protocols existing in the industry. There's a method to do flexible multiplexing, so you don't have fixed containers, so that, again, raises the effectiveness of the wavelengths usage. And you have exceptional SLA tools because you have both performance monitoring and you have uniform OTN FEC integrated performance monitoring. The other option is to do it in carrier Ethernet aware max ponders, adding a integrated carrier Ethernet switch, preferable to have low latency. Bit error rate standard in the industry, only Ethernet, and what's important here that you can have oversubscription. That's native to Ethernet. It's basically you can have more interfaces more access interfaces than your final optical line, because you're assuming that not all the users are going to use the line at the same time to the maximum committed rate. And the beauty is that you have extended standard carrier Ethernet SLA assurance tools, both performance monitoring and the OEM that we already talked about. I assume that it's going to be the same choice like before, so we'll jump over this. Touching slightly on 100 gig, and that's very, very limited. That's not the focus. We see in 2014, first of all, dense access pluggables. We have the CFPs, and some companies, some optical companies jumping even over CFP2 and going straight to CFP4 and QSFP, and then repackaging the smaller packet into a CFP2 and a CFP. We see the emergence in 2014 of 100 gig DWDM coherent CFP. So coherent CFP becomes common technology and pluggable. And of course, re-emergence of the metro CFPs, the 4x28, at better performance and lower cost. So in 2014, the 100 gig technology is going to become not commodity, but common. It's not going to be something that is difficult to achieve. It's going to be difficult to pay for, and it's going to be a pluggable technology like the 10 gig today. We are basically at an inflection point where 100 gig DWDM will cross the 10 by 10 gig barrier. So it's going to become affordable and normal technology, and it's going to move finally into the metro and data center interconnect. Transport, same story. You can plug the CFPs straight into your switches, like any other pluggable. Or you can do media conversion, transponding, and maxponding. And just a flavor of what we dream about having in 2014, comparing the 10 gig fixed or tunables and the existing CFP Metro. We see the ones in blue, next generation of the CFP Metro, better performance, both 50 and 100 gigahertz, both fixed and tunables, and much better cost structure. And very important to see the coherent CFP that, again, comes with two flavors. One is matching the 10 gig optics, and the other one for long haul or medium haul, I would say, 1,000 kilometer and about around 1,000 kilometer. Now, we talked about simple networks, and I would like to give just a flavor of the complexity that maybe was mentioned here. This is the beginning of the optical networking. We can go to dynamical optical network where we have not just transponders, but multi-degree ROADMs. We are 10 gig and 40 gig and 100 gig and beyond ready. We are doing the effective subwavelength aggregation. We use maxponders and transponders, and we use tunable optics. We use dynamic wavelength allocation and reallocation. So what are the services and benefits? First of all, automated self-inventory. The network, it's your database. You're discovering the network, you install it, you discover, and that's your database. Second, you want to do a service activation, you just point and click, I want this service, the network is going to do it for you. It's intelligent. And if you need to do any pass service or you have any failure, you basically provision alternative pass, and this is going to be done for you by the network. In general, it's a self-managed and self-healing optical network, and that basically leads to reduced operational cost. It's going to cost a little bit more. Finalizing, going back to the simplicity. When you look at do-it-yourself of this type of networks, look at the capability to implement from the simplest to the highest from media conversion to DWDM. It's interesting to have the same elements doing both converters and multiplexers and transponders and muxponders, not different tasks. Look for adaptability from 10 gig to 100 gig and look into the future. 200 gig and 400 gig are probably a few years away. It's important to have insurance, and that's basically the SLA assurance management and deployments, debugging tools. If everything goes well, you don't need those. If anything goes wrong, you should be able to look at the performance monitoring and see where the packets or your traffic it's disappearing. You should be able to look at the optical signal quality, to look at the transmit level, receive level, like we showed here, and to understand why your optical design doesn't work. You should be able to look at, and that's the digital diagnostic, you should be able to look at the eye-grade mask. That's a famous picture that shows the quality of the signal. It should be an open eye. Now important, and that's very common in carrier Ethernet, is to have traffic generation and checking. In carrier Ethernet, packet generation and checking, it's now very common, started probably quite a few years ago, and it's very common in the industry. We see it moving to layer 1, doing bitstream generation and checking. And that allows you basically to test your network at turn-up without needing any testing equipment, and doing it fast because you can test all your wavelengths that you want to activate at the same time, and see that the link is fine. And lastly, look at your monthly operating expenses. You're going to pay for your rack space, you're going to pay for the power consumption every month, and those are elements that we feel that are important to watch. Any questions? We are off the hook. Oh.
I know it's not exactly in your presentation, but I would like to hear something about what yourself and other vendors are doing on the path forward to 400 gig and terabit. And I'd also kind of like to speculate a little bit beyond that. So we're starting to approach some pretty significant practical physical limitations within the fiber. So there's only so much bandwidth you can stick on a single mode fiber before the wavelengths get short enough that the single mode starts to behave like multimode. So I'm just kind of curious, what is the far reach of the industry at this point?
That's a good question. I think it goes beyond the scope of this presentation. It's more for an optical technology and not for an optical system. But there's no question that we are looking, we as a company are looking at next step of 200 and 400 gig and probably 1 terabit. Beyond this, not yet. Not in our scope. We'll wait for the industry. I'm sorry to disappoint you.
Is there like a speculative timeline of when 400 or terabit is anticipated to be at least
Gigabit.
Well,
400 gigabit, not
400 and 1,000.
Yeah, I think that
Is there a speculative timeline of when this will be something that we can implement in a lab, if not necessarily make available?
I think that you can have 400 terabit trials. You have them today, not from MRV, but from other companies. We foresee the 200 and 400 gigabit to be a common technology in late 2015, 2016, beyond simple trials. So 2 to 3 years from now, what we foresee now, we see now the 100 gig moving from the level of fancy technology to something that is common, with the emergence of pluggable CFPs for coherent 100 gig. And we expect the same phenomena to happen for the 200 and 400 gig probably in 2 to 3 years. Yeah, I'm talking about 200, 400, and terabit. Those I foresee to become a common technology, not deployed not just by Comcast in the long haul, in the backbone, but in the data center, maybe in the enterprise 2 to 3 years from now. Because that's, at least from my point of view, our sweet spot, not the Comcast. We saw the desire to be there, but not for us, not today. Yeah, Manix.
How do you decide between which of the architectures are easier to operate? You had OpEx up there, and maybe that was space, power, and cooling. But when it comes to providers' actual ability to operate the networks, how do you decide which is easier?
I didn't quite understand your question. So we have space, power, and cooling. That's something that you always have to have in mind, and do your best with what is offered in the industry.
Well, there's the concept of complexity in the network. And networks that are more complex, we inherently believe to be more expensive to operate.
Absolutely.
And I've struggled with this, is there a way to quantify that? How do you characterize complexity and therefore make the decision which architecture is more simple and therefore cheaper?
Yeah, that's a very good question that I will pose to the public, because you guys are the users, yeah? I see you guys as the users. Same way that I pose the questions about selection between putting the optics in Ethernet switches and using an optical transport. I think that we as suppliers would like to sell you the most complex network, because that's how we are going to make the most revenues. So that's a very fair question, and I think that you can ask your peers.
Okay, well, actually, I'm from Siena, so I'm from a vendor.
I understand.
And so if anybody has a good answer to that question, I'd be very interested in it.
Again, depends on the application. Keep in mind that we looked here at simple point-to-point applications, and we just showed the dynamic optical transport as a possibility. But the basic of the optical design was focused on simple point-to-point applications, where you can even entertain the choice of putting the optics straight into the routers.
Well, as Matt Petak from Yahoo, I'll answer from the perspective of someone actually putting optical networks in place. The question is sort of meaningless, because it's going to depend upon what point you look at a network. And networks evolve over time, where we start off with a solution that has transponders as external units. We tended to migrate from external transponders to integrated optics within the router platform. And you have kind of the pendulum swing of, okay, the external transponder makes sense initially, then the optics technology gets better and better. You put the integrated optics into your routers, you reduce the operational complexity of your network by reducing the number of boxes that you're dealing with in the network. Then the bandwidth demands go up, and you start to find that the integrated optics aren't supporting the next generation level of speeds that you need. So you go back to external transponder units again, and an external transport network that actually has the speeds and the distances you're looking for. Your 100 gig coherent wasn't in the routers initially. So you do your external boxes, you get your 100 gig coherent in the long haul. Then you start getting the manufacturers that start saying, hey, we've got integrated coherent CFPs. Now you can move it back into the router, reduce complexity in your network. So it really is, at what point are you looking at a network to say more complex, less complex, more OpEx, less OpEx, more CapEx, less CapEx? In an ideal world, we'd have a really cheap box that had infinite bandwidth and low complexity, low OpEx, low CapEx, hey, we all make money hand over fist, doesn't exist. Physics is not always our friend. So sometimes we have to go with the higher complexity just because that's what physics is providing for us in the technology space.
Thank you. Okay. Thank you.